Here's some notes for you about circular motion. Before you look at these notes, you should have some experience collecting data yourself and looking at what what the relationship is between unbalanced force and the speed something is going when it's moving in a circle, the radius of the circle, and the mass of the object that is moving in a circle. So if you haven't done that lab exercise yet, then you have got here too early. Assuming that you have done that, let's talk about those things. Now, first of all, we're going to be interested in circular motion at a constant speed. So you can imagine if you're driving in your car and you put the cruise control on and you turn the steering wheel a little bit, you're going to go around in a circle, right? Now you might be thinking to yourself, okay, Mr. McGrath, why are we talking about unbalanced force if we're going at a constant speed? Because doesn't constant speed mean that that there's no unbalanced force, that the forces are balanced? The answer is no. If the forces on something are balanced, then it is either at rest or moving at a constant velocity. Constant velocity means the cruise control is on and the steering wheel is pointed straight ahead. Constant velocity is constant speed plus constant direction. So if something's moving in a circle, like that doesn't happen for free, right? If you think back to broom ball when we first started looking at forces, if you want that bowling ball to start turning, you can't just like watch it and hope for the best. You got to start tapping it. When we have circular motion, the unbalanced force toward the center of the circle. And not only that, but we know how that unbalanced force, because of the lab, when you collected your data for unbalanced force versus, what's the first one that I had you do? Maybe mass was first. Unbalanced force versus mass. The more mass you have, the more unbalanced force you're going to need to move something in a circle. And that turned out to be a linear relationship. When we looked at unbalanced force, versus speed, that was not linear. The faster you go, the more unbalanced force you need toward the center of the circle, but it went up like this, and it turned out to be a square model, right? So like unbalanced force depends on v squared. Unbalanced force depends directly on mass, like mass to the first power. Unbalanced force depends on speed to the second power, and the radius, the bigger the circle is, the less force you need, because the bigger the circle is, the more it kind of becomes straighter and straighter and straighter until you can hardly even tell you're going in a circle at all. So that looked like this, and that is an inverse relationship, like unbalanced force depends on 1 over r. If you put these together, then we have unbalanced force. Now, I'm not just going to write unbalanced force here because we know unbalanced force equals mass times acceleration, Newton's second law. This is specifically for circular motion. So I'm going to say unbalanced force for circular motion is equal to, it's directly proportional to m, directly proportional to v squared, and inversely proportional to r. The data that you collected in your lab exercise should have pointed you to these three relationships, and when we put those together, this is what we get. Okay, so what do we do with that? I'm going to show you a couple examples of what force diagrams are going to look like, and show you that force diagrams are really important in being able to deal with circular motion situations and solve the kinds of problems that we want to be able to solve. So here are some examples of just the force diagrams. So how about a car driving over a hill? I'm going to make a little dotted line there to represent the hill. And there's my car right there. So what forces are there acting on the car? Well, if the car was just going on a flat road, the force of gravity and the support force, or the normal force, pointing upward. Of course, gravity doesn't care what's happening. Gravity's just doing its gravity thing. Downward force. If you wanted to know how much force of gravity there is, you would take the mass of this car and multiply it by 10, right? Now, what about the support force? Is it equal to this? No, it's not. Where is the center of this circle? The center of the circle, which I'm going to make in my force diagrams, I'm going to make a little X there. That's where the center is. So we know that when we have circular motion, there must be unbalanced force toward the center of the circle. That means that wherever the center of that circle is, that is the winning direction. So that means that gravity must be winning versus the normal force, right? And then if we wanted to write the unbalanced force equation, we would say unbalanced force is equal to the force of gravity, winner, minus the normal force, which is the loser. Toward the center of the circle is always going to be the winning direction. If this seems weird to you and you're like, wait, I've been in a car and I've driven over a hill before. If you've driven over a hill fast enough to notice this, then you probably have had the experience where you feel like a little lighter and you kind of like have that woo sort of feeling. Don't really have a better way of describing it than that. Likewise, let's say the same car is driving through a dip in the road. How much gravity is there? The same as there always is. The force of gravity is not going to change. But now the center of the circle is up here. So actually, make it a little higher. This, toward the center of the circle, must be the winning direction, because there must be unbalanced force towards the center of the circle. So where's the center of the circle here? That means that is the winning direction, which means that the support force is bigger. So in that situation, unbalanced force is equal to normal force, winning, minus gravity, losing. I'll give you one more very common example. These are going to be the three most common ones that you see. We have a car driving around a corner. Now these are like side views. This is going to be like the head-on view. Like the car is headed right toward us, going to run us over. Except it's not going to run us over because it's turning in a circle. Which way is it turning? Let's say it's turning, let's see, if it was coming this way, then from the driver's point of view, that would be turning left, I guess, right? So let's say that the center of the circle is here. Again, notice I'm always going to put a little X there where the center of the circle is. Now, here's the force of gravity. Here is the normal force. Now these, in this case, the car is driving around a corner. The center of the circle is not up here or down here. These are balanced, right? If the center of the circle was up here, like in this diagram, then the normal force would be bigger. If the center of the circle is down here, then the normal force would be smaller. Here the center is over here on the side. So what is the unbalanced force? Like, what is pointing toward the center? There's got to be something, because, as you know, your car can actually turn in a circle. So what is it? Well, it's the friction force. If you're wondering to yourself, well, how come you didn't put the friction force in these diagrams? Well, you know, there's some traction from the car and there's some resistance, but since the car, we're assuming the car is going at constant speed through these, those relatively small forces are going to be balanced there. It doesn't play into the calculation when we're trying to figure out what's going on toward the center of the circle. Just like in this example, these aren't going to matter, except for the fact that we know that friction force depends on normal force. Remember, friction force is that coefficient of friction times normal force. That's back from, I suppose that was in Unit 5. So here, in the direction toward the center of the circle, there's only friction winning and nothing is losing. So the unbalanced force here would be equal to just the force of friction minus nothing. There's nothing losing there. And you know that you do need that friction. Like if you're driving along on a patch of ice and you try to turn, what happens? The car just keeps going straight. Why? Because there's not enough friction to be able to supply that unbalanced force toward the center of the circle. So the car doesn't move in a circle, it just keeps going straight. Okay, so in each of these examples, if we had some numbers, we would go ahead and replace the unbalanced force here, since we're doing circular motion, with mv squared over r. And I should add here, let me go back in your notes and just add here that since unbalanced force is equal to mass times acceleration, always, that's Newton's second law, if I put mass times acceleration here, then the mass would cancel out on both sides of that, and I would get acceleration, if you're moving in a circle, is equal to v squared over r. It's the same exact equation as this, just without the m there, because force equals mass times acceleration. Right, that's all. All right, so I'm going to do an example for you with some numbers. I'll do examples. Actually, I'll do 3 quick examples here. So for this one, we'll say car over a hill, and in all 3 of these, let's make the mass of the car 1,000 kilograms, and let's make the speed of the car equal to, let's see, how about 20 meters per second, that's about 40 miles an hour-ish. And let's make the radius of these equal to, how about 200 meters. And then for this one where the car is going around the corner, let's make the, well, I'm going to do a different one with that actually. So we'll leave that for now. But for these ones, let's say the radius, both of going over this hill and through this dip, the radius is 200 meters. So for the car over the hill, we want to find the support force from the road. Now, just looking at our diagram here, if the car is going over the hill, gravity must be winning, and gravity would be 10 times this, it would be 10,000. So whatever this comes out to be, it better be something less than 10,000, because I know that this has to be the winning direction. So starting from here, unbalanced force is equal to gravity minus normal force, because toward the center of the circle has to be the winning direction. So now unbalanced force when you're moving in a circle is mv squared over r is equal to the force of gravity, which is 10 times m minus the normal force. So the normal force, if I do a little rearranging there, algebra-like, I get that the normal force is equal to, I'm going to add that over there and then subtract this. So 10 times m, that's 10,000. Sorry about that random dot there. Oh, weird looking. Looks like a semicolon. That's just 10,000 minus mv squared over r. M v squared over r. So 10,000 minus, let's make it look all fancy like with a little fraction there. mv squared over, oops, don't want that there, I want to put that here. And that is 8,000. And that's about what we should have expected, right? This is 10,000 here, and this is 8,000. There's less. So what does that mean? Well, it means if you're a passenger in that car, you feel a little bit lighter than you usually do. Now, what about if you're going through, that's not really how you spell through, it's just a little shortcut there, through the valley. Well, if you're going through the valley, then unbalanced force is equal to, now the support force is winning because that's where the center of the circle is, up. So mv squared over r is equal to the normal force minus 10 times m. So we get the same kind of shuffling around here, but now I'm going to add those together instead of subtract them, right? That's what the algebra is telling me to do. And if you do that, you're going to get that this time, instead of being 2,000 less than the force of gravity, it's going to be 2,000 more than the force of gravity. So if this is what's going on, you're going to feel a little heavier, right, at the bottom. And you probably know that from experiences on roller coasters and other carnival type rides. So I'll tell you right now, the most common mistake that I see with introductory physics students such as yourselves doing this kind of problem is like circular motion. They're like, okay, unbalanced force equals mv squared over r, and they do that and then they're done. But that's not the end of it, right? mv squared over r is equal to, in this case, the force of gravity minus the normal force. In this case, normal force minus the force of gravity. So you do have to find this, mv squared over r, but you have to know from your force diagram what it's going to be equal to. So just be careful with that, please. And in this case, if we knew, I'm going to leave this one, I won't do this one with numbers, so I'm going to keep this under 20 minutes for you. But this mv squared over r, my unbalanced force, would be equal to, and the force of friction would be mu times the normal force. And the normal force in this case is just equal to the gravitational force. So that would be equal to 10 times m. So you can do those problems too. Those are the three most common types of circular motion problems that we're going to see. There'll be a few variations on that too.